All right, so in this video, I'll talk about manifolds. So roughly speaking, manifolds are topological spaces that locally look like open parts of Euclidean space. In case you want to do calculus on such manifolds, then you also need a additional smooth structure. In this video, I'll try to motivate these two concepts and also explain what they are. Okay, so let's start. So as I said, you start with a topological space and you make some reasonable assumptions. Why not assume Hausdorffness, meaning 2 points can be separated by open sets, and also assume second countability, meaning your topology has a countable base. Okay, so M is a topological manifold if it's, as I said, locally Euclidean. So this is what that means. So M is a topological manifold if it's locally Euclidean. So if there exists an open cover U alpha, so the union of the U alphas is equal to M, and charts that are homeos between U alpha and some open parts of Euclidean space. So some charts, so there also exist charts which are maps of U alpha into some V alpha, these being open subsets of R to the N. And these are homeomorphisms. So their inverses are also continuous and the map themselves are continuous. So these, each separate map is called a chart. The collection of the charts is called an atlas. Perhaps we can say in words a few examples of topological manifolds. Everybody needs to know about the circle, the sphere. So the sphere has two charts, making it into a topological manifold. You get one chart by stereographic projection from the North Pole and another chart doing stereographic projection from the South Pole. One thing I forgot to say here is that N here is fixed for every chart, and it's called the dimension of the manifold. Now, next I want to talk about how you put a smooth structure on your topological manifold. But before that, let's talk a little bit about continuous functions. So let's pick an open subset of M. And let's spend some time with continuous functions on W, which are functions. Now, on topological manifolds, you can understand continuous functions locally. So what does that mean? Well, if you cover W with some charts, so I will call them U alpha K, but you can pick a different cover, that's perfectly fine as well. Then a function f from M to R is continuous if and only if f is only locally continuous, which means what? Well, if you compose f with a inverse of a chart, then you will get a map from phi alpha K takes a minute to get these sets right. Okay, and you can do this for every K here in your cover. Now, let's call these maps, say, FK. Being locally continuous means that each of these FKs is continuous wherever defined on this set. Okay, now continuity obviously does not depend on the choice of U alpha K here. And this is what you need to note here. Maybe a quick exercise for you. You get that So on the right-hand side, local continuity does not depend on choice of U alpha k. Okay, this is going to be important because next, in order for me to do some calculus on my manifold, I need not just continuous functions, but smooth functions, right? So you attempt to define smooth functions on W. So C infinity W, right? So you attempt to do this in the following way. So following the analogy from the top, you ask C infinity W to be functions from W to R. Sorry, also here, I meant W to R. So you ask C infinity W to be functions from W to R. And here instead, you ask these FKs to be not continuous, but smooth. So this makes perfect sense because this set here, this set is an open subset of R to the n. So it makes sense for me to ask for this FK to be smooth. Now, unfortunately, even though you can do this, this definition here, unless you impose further conditions on M, will depend on the choice of cover. So depends on choice of U alpha k. So one way to make sure that this is not the case is asking that M has a smooth structure. So maybe I can talk about that here. So need smooth structure, because again, we are not satisfied with this. Maybe I can put like a big X here. This is not okay. So need smooth structure on M. So the smooth structure will consist of the following condition. So you ask that the phi betas composed with the phi alpha inverses. Again, these will run from U alpha So you ask that each of these maps is a smooth map. For all alpha beta. So maybe you can call this a condition star. So M topological manifold plus condition star is what we call a smooth manifold. All right, and then the advantage of this, if you ask for star here, then the definition of C infinity W will no longer depend on the choice of cover by charts. This is easy to verify. All you need to take a look at here is the definition of the FKs. So in the problem is in the FKs, when you transition from one chart to another, when you transition here from one chart to another, then you will always pre-compose with a map like this. Now, if all the maps like this are smooth, then by the chain rule, the switch from one chart to another will also just stay smooth. All right, good. So perhaps a quick remark here. So if all you cared about, for example, are C1 functions, then here, instead of smooth, you would ask only for C1. That means just continuously differentiable. Now, in that case, the condition star here would be that these maps are not smooth, but C1 maps. So meaning all their partial derivatives are continuously differentiable. And then you would arrive at the notion of not smooth, but C1 manifold. Analogously, you can define C1, C2 manifolds. If you want to work with holomorphic functions, right, in that case, you introduce here maps from W to C, and you ask for the F case to be holomorphic. Again, this will be open cover dependent. If you want to get rid of this, then you ask for each of these maps here to be holomorphic. All right, and then you would get the notion of holomorphic or complex manifold. So again, it all depends on what kind of calculus you want to do on your manifold. All right, thank you for your attention.